Hello, my name is Dr. Steve Anton. I am a professor of mechanical engineering at Tennessee Tech University, and I'm really excited today to give you a tour of my lab and show you some of the really cool research that we have going on. So I'm here in the basement of Brown Hall on campus, which is the center of mechanical engineering here at Tech, and we are at the Dynamic and Smart Systems Lab. So let's go ahead and come on in and let's take a look. So first, let me kind of give you an overview of the lab. The bird's eye view, you can go ahead and take a look around at the lab in general. So in the Dynamic and Smart Systems Lab, we focus our work on smart materials and smart structures. In particular, we look at dynamics of smart materials. So these materials can be used as sensors, as actuators, even to harvest energy from the environment. And typically, my background is in vibrations, so typically we're looking at dynamic systems, systems that are moving, oscillating, that type of thing. So we use these materials, mainly we deal with a material called piezoelectric material. It can be used as a sensor and as an actuator. It's really handy. So let's go ahead and take a look. I'm very excited to show you some of the cool research areas that we have going on in the lab. So first off, I'm going to bring you over here and talk to you a little bit about the biomedical work that we have going on. So for the last several years, me and as well as all of my graduate students and undergraduate researchers have been doing work with the National Institutes of Health, funded by NIH, looking at integrating these smart material sensors into biomedical devices. And in particular, we're focused on knee replacements. So let's take a look at some of the work here, and I'll talk you through this. So here, I've got a mock-up of a total knee replacement. And here you can see a typical femur and tibia. This is the thigh bone and the shin bone. So when this joint starts to fail, what they'll do is replace it with these components. So this is a mock-up, but here we have some of the real components. So this is the femoral component. It replaces the bottom of the femur. It's typically metallic. This is a polyethylene bearing that goes there at the interface. Gives it a nice smooth surface and gives it something to rotate on. And then below this is a tibial tray, okay, which looks typically something like this. So the bearing sits in that tray, and this tray gets inserted here into the tibia. So these are real components that we got from our surgeon collaborator, and what we're working on is specifically integrating sensors into these bearings. So this is a real one, but what we've done is started to look at 3D printing of our own bearings. So this is a 3D printed bearing. And here we've got several of these piezoelectric transducers placed within the bearing. And the way these materials work, here's some raw piezoelectric materials. As you compress these, they'll actually generate charge and voltage. So you can measure, you can use them as a sensor. You press on them, you input a force, and they'll output a voltage. So here we've got various instrumented bearings that we've placed in a load frame and applied load and been able to measure the balance of forces in between the components of the knee. So one of the keys, if we look at this example of our smart knee, is if you've got, for example, more force in one compartment than the other, that would tell you that you have some sort of an imbalance in your knee. This is really important for the medical community. So that's really what we're working on. Now, another thing that's exciting about these piezoelectric materials, here's another example of what these look like, is they can also be used as actuators to send energy into the system. So that's what we have over here. Again, that same tibial tray, we have a few of these. Instrumented with these piezoelectric transducers. And what's so exciting about this work is the ability to detect if one of these trays comes loose from the tibia. Because this can happen. This is a failure mode that the surgeons see, and then they'll have to go in and fix the surgery. They'll have to do a revision. So here we've artificially created these samples using real components but a synthetic bone, and we've intentionally failed the interface, made it loose, and we send energy in with the piezoelectric and interrogate this interface, and we can detect when this thing is loosened. We're currently working on machine learning approaches to try to detect loosening of this interface by really looking at all the data we can get from the sensor and combing through all the different failure modes. And then finally, moving on to some other exciting work that we're doing with some 3D printing is looking, instead of putting sensors in the knee joint, putting them inside a flexible insole for a shoe. And this is useful because sometimes we want to have sensing outside of the body, and we can custom print these to fit any foot shape. So here is kind of your normal foot, regular arch. This would be like a high arch or a flat-footed case. And if you're one of these cases, it can be difficult to find an insole that would fit your shoe correctly, particularly one that has sensors embedded. So we're looking at embedding commercial sensors here, various types of these commercial sensors, into these flexible filaments that we can 3D print, as well as fully printing our own. So this is a fully printed sensor, not a commercial sensor, all using flexible 3D printed materials, and this could be integrated directly into the insole itself. So very exciting project here, and that leads us into our 3D printing area, which is here. So we've got 3 different 3D printers. First, this is the Forms Lab. It's a SLA printer, stereolithography, and we can print a lot of different interesting materials here. We've used these to print different bearing materials to evaluate their performance. We also have a standard FDM printer here. This is the Lulzbot TAS6. We've been printing some components for face shields recently. But this is a FDM printer, so your standard where it loads a filament, melts it through an extruder. And then we also have this printer, a Nano 3D print, which is really exciting. Very cool printer that also has here an area where you can put a syringe and inject liquid. So what we're looking to do with this is actually print. It has an FDM head as well. So you print a base plastic and then you deposit a liquid, conductive liquid, to print a circuit on top of the device. Pretty cool. So that's our 3D printing area. Over here we have our general equipment cabinet, lots of different general lab equipment, oscilloscopes, power supplies, function generators, data acquisition systems. This is like the brain of the operation. All of our data comes from here, from equipment in this cabinet. And then I mentioned that DSSL is, we work on dynamic systems. And so over here, what we have is a machine fault simulator, machinery fault simulator, where we can turn this machine on, get it rotating, and intentionally cause damage to the shaft, put in a worn bearing, have something out of balance, and see what happens in a rotating machine. And we can use our smart material sensors to try to determine when this rotating machine is going bad. So we can try to get ahead of it. Instead of doing some time-based maintenance, we can do what we call condition-based maintenance and get ahead of it, repair it before anything catastrophic happens. Also, we have some really exciting equipment over here. This is a laser vibrometer. It is a non-contact laser-based sensor, and I have a quick demo set up for you. So here's a cantilever beam. It does happen to have a piezoelectric sensor on it, and instead of putting something heavy like an accelerometer on the end of the beam to measure its vibration, we have this laser-based system here, and it's non-contact. You can see the laser shining on the beam. Here's an oscilloscope. I have it connected to the laser. Right now the beam is not plucked, but as soon as I pluck it, you'll notice I get a signal on the oscilloscope. So we can measure the dynamic response, the vibrations of this beam without even touching it, just shining a laser. Pretty neat stuff. Over here we do have a fabrication area where students oftentimes will come use this mill lathe combo to fabricate their own experimental setups. This is an example of some drawings a student was working on this week for a clamp to hold one of those beams, just to give you an idea. So we do some in-house fabrication. And then finally, the last room I want to show you is in here. So this is our dynamic room. This is a highly dynamic room. I say that because we have this gas gun experiment in here. So we built a gas gun, relatively low pressure, but what this does is we fill this with air. When we fire the solenoid, that air expands into the launching barrel and launches a projectile down the barrel at this interface, and it will hit this interface. And we've got our sensors, our piezoelectric sensors, right here on the beam, and we're trying to detect the instant that the projectile touches. And we're trying to see how fast, how instantaneously we can detect that something has changed in this interface. And this is useful for any kind of structure that would operate in a highly dynamic environment, things like earthquakes and blasts, and these types of things. So we do some really high rate, very fast data acquisition and signal processing, and we use some really state-of-the-art equipment. This is National Instruments PXI analyzer that has very fast data acquisition cards for streaming data, processing that data. This is kind of the workhorse of these experiments. So that gives you an overview of the DSSL lab. I hope you found